Ever watched a movie and wondered, how did they get that impossible camera angle? Or seen a robot navigate a room and thought, how does it see things from different perspectives? Today, we're diving into a groundbreaking AI breakthrough that's rewriting the rules of dynamic view synthesis, the magic of turning a single video into multiple realistic camera angles. Think of it as giving a computer the ability to think backwards and create whole new worlds. Let's break it down. Dynamic view synthesis, or DVS, is the art of generating new perspectives from a single video. Imagine watching a scene and suddenly seeing it from the back, the side, or even above, like a superhero with X-ray vision. But here's the challenge. Traditional methods relied on 3D models, massive datasets, or expensive reshoots. It was like trying to build a house with only one brick. This research flipped the script. Instead of building complex 3D models, they treated DVS like a puzzle, working backward from noise. They used a video diffusion model, an AI that generates videos by iteratively adding and removing noise, like a painter refining a canvas. But here's the twist. They didn't tweak the model's brain or add extra parts. Instead, they manipulated the starting point, the initial noise. But here's the catch. Removing noise from a video risks losing critical details. Think of it like fixing a blurry photo. Too much sharpening and you end up with artifacts. This is called zero-terminal SNR collapse, where the final noise removal step becomes pure static, wiping out the original scene. So how do you fix a blurry photo? The researchers invented K-order recursive noise representation, K-RNR. Imagine building a house where each layer depends on the one before it. K-RNR recursively refines the noise, gradually aligning it with the original scene's structure. It's like giving the AI a better memory for what the scene should look like, even as it adds new details. But what about areas the camera can't see? That's where stochastic latent modulation, SLM, steps in. Picture the AI peeking around corners by analyzing the existing image and guessing what's hidden. SLM uses context-aware sampling to complete occluded regions, making new views feel natural, like filling in the blanks of a mystery. Now, let's talk about the math behind the magic. Building a video reconstruction model is like training a digital artist to recreate a video from scratch. The big challenge: deciding how many times to refine the video step by step. Too few steps and it's blurry. Too many and it falls apart. Here's where the research gets interesting. They tested a parameter called K, which controls refinement depth. When K equals 3, results were near perfect. The video looked almost identical to the original. Even at K equals 7, it worked well, but pushing to K equals 8 caused issues. Why? Too much refinement likely added noise or overcooked the video, like editing a photo so much it loses its soul. Another key player, the adaptive reference latent index, or delta. Think of delta as the model's internal ruler for comparing video parts. Testing values from 1 to 7, they found delta equals 3 was the Goldilocks zone, crisp details, natural motion, and that all-important real feel. Too low, delta equals 1/2, and the model lacked guidance, leading to blur. Too high, delta greater or equal to 4, and the reference point diverged from the actual video, causing instability. Finally, they pitted their method against others. Some models struggled with motion or identity when cameras moved. Others were slow, overprocessing data. But this approach, it nailed both quality and speed. It's like finding the perfect recipe. Too much of one ingredient and the dish falls apart. So what's the takeaway? Building better AI videos isn't about throwing more steps or parameters at the problem. It's about balance. It's like tuning a guitar, too tight and it snaps, too loose and it sounds off. In this case, the sweet spot was K equals 3, and delta equals 3. Next time you watch an AI-generated video, remember, there's a whole lot of math, experimentation, and balance behind that smooth, realistic look. Thanks for sticking with me, stay curious, and I'll catch you in the next one.